The James Webb Space Telescope, JWST, is a 6.5 meters diameter cold space telescope with cameras and spectrometers covering 0.6 micrometers to 28 micrometers wavelength. Launched on December 25, 2021, it orbits the Sun-Earth L2 point and extends the discoveries of the Hubble and Spitzer space telescopes. JWST enables observations of the distant early universe, potentially reaching beyond redshift z equals 15, within 300 million years of the Big Bang. This document provides an overview of JWST's history, mission, scientific objectives, and technical performance. 26 years ago, a small committee report called for an infrared-optimized space telescope with an aperture of at least 4 meters. With support from the US, Europe, and Canada, 20,000 people realized that vision as the 6.5 meters James Webb Space Telescope. The telescope is working perfectly, with much better image quality than expected. This report summarizes the history, concept, scientific program, and technical performance of JWST, citing detailed reports on the design and measured performance on orbit. JWST extends the discoveries and technologies of the 2.4 meters warm Hubble Space Telescope and the 85 centimeters cold Spitzer Space Telescope. It enables observations of the distant early universe, potentially reaching beyond redshift z equals 15. JWST's infrared wavelength range penetrates dust clouds to observe obscured active galactic nuclei and star and planet formation. It shows objects too cool to radiate visible light and includes fundamental vibration rotation bands of important molecules. JWST was conceived from the beginning as an international project, led by NASA in partnership with the European and Canadian space agencies, ESA and CSA. Observing time allocations are open to all astronomers worldwide. JWST was launched from French Guiana on an ESA-provided Ariane 5 rocket. It cost NASA $8.8 billion to get to launch and will make observations for a projected fuel-limited lifetime potentially as long as 20 years. JWST's observations cannot be obtained in any other way. Compared to Hubble, it has 6.25 times the collecting area. Unlike Hubble, which emits its own infrared beyond 1.7 micrometers, JWST is a cold telescope. Spitzer was cold but at less than 2% of JWST's collecting area. For ground-based telescopes, the Earth's warm atmosphere results in a background that is 10 to the power of 6, 10 to the power of 7 times higher and also blocks large regions of IR wavelengths. JWST includes a general-purpose instrument package in its Integrated Science Instrument Module, ISIM. This includes NIR-CAM, covers 0.6 micrometers to 5 micrometers with filters, a coronagraph, and simultaneous observation in short and long wavelength bands. NIR-SPEC covers the same wavelength range with prisms and gratings, fixed slits, an integral field unit, and a micro-shutter array. NIR-ICE covers the same wavelength range with slitless spectroscopy and a non-redundant mask for coronagraphy. MIRI covers 5 micrometers to 28 micrometers with imaging, IFU spectroscopy, and coronagraphs. Fine Guidance Sensor, FGS, senses pointing errors and feeds the attitude control system. The JWST project involves significant international contributions. ESA provided the NIR-SPEC, with detectors and micro-shutter array from Goddard, and the launch vehicle. CSA provided the NIR-ICE and FGS. A partnership of JPL and a European consortium provided MIRI. NASA funded NIR-CAM and the US portions of MIRI and NIR-SPEC. JWST's first year of observations includes nearly half a year of guaranteed time observations for instrument teams, interdisciplinary scientists, and the telescope scientist. 13 competitively selected directors' discretionary early release science (DDERS) programs with immediately public data. 286 programs selected through dual anonymous peer review, including 263 pointed programs, 3 pure parallel programs, and 20 archival or theory programs. The Cycle 2 call received more than 1,600 proposals submitted by over 5,000 scientists worldwide. JWST is a technical pioneer, featuring several groundbreaking innovations. First deployable segmented space telescope. Mirror segments aligned and focused after launch. Cryogenic optical system providing diffraction-limited images as short as 1.1 micrometers. Larger and more sensitive detectors than previous generations. 6.0K cryocooler for MIRI with no expendables. Cryogenic ASICs to control and read near IR detectors. 5-layer sunshield cooling the telescope to between 35K and 55K. In the 1980s, preliminary work on an 8 meters to 10 meters passively cooled infrared telescope began at Space Telescope Science Institute. The 1989 SHE/NASA Next Generation Space Telescope Conference excited scientists and engineers with the possibilities of a large cold infrared space telescope. During this decade, other significant developments included 1979, NAS report recommending the Shuttle Infrared Telescope Facility, later Spitzer. 1983, EROS launch. 1989, COBE launch, beginning the era of precision cosmology. The 1990s saw several key events in the development of JWST. 1990, Hubble Space Telescope launch and discovery of its optical error. 1991, Bach-Hall report endorsing Spitzer and declaring the 1990s the decade of the infrared. 1993, Edison mission proposal to ESA for a deployable 2 meters plus diameter IR telescope. 1995, HST and Beyond Committee report on potential successors to HST. 1995, JPL's Mirror's proposal for a passively cooled mid-IR telescope. On October 30, 1995, NASA initiated a study of the Next Generation Space Telescope, NGST. Key events in this period included Bernie Siri chosen to manage the NGST study at GSFC. January 1996, release of the Hubble Deep Field Image, changing views of galaxies in the universe. January 1996, Dan Goldin's speech at OS, challenging for a 6 to 7 meter telescope. May 1996, final Dressler report on HST's successor published. The late 1990s saw increased industrial involvement in NGST development. 1996, NASA issues cooperative agreement notice for company studies. 1997, formation of ad hoc science working group. 1997, ESA establishes NGST task force. 1998, NASA selects Lockheed Martin and TRW for phase emission studies. 1999, microshutter array recommended for multi-object spectrometer. The ASWG final report recommended including NIR-CAM, NIRSpec with a MEMS-based multi-object spectrograph, and MIRI for both imaging and spectroscopy. The early 2000s saw crucial developments in defining the JWST project. 2000, Decadal Survey ranks NGST number 1 in large space missions. 2001, telescope descope from 8 meters to 6.5 meters diameter. 2002, TRW chosen to build the observatory, NGST renamed James Webb Space Telescope. 2002, selection of NIR-CAM team and flight science working group members. 2002 to 2003, MOS signed with ESA and CSA for international partnership. This period saw significant progress in JWST's design and construction. 2003, beryllium selected as mirror material. 2004, fabrication of flight mirrors begins. 2003, Spitzer Space Telescope launched, demonstrating power of mid-IR space missions. 2004, official construction of JWST begins. 2005, Bellows Pulse Tube Cryocooler chosen for MIRI. 2006, detailed JWST science objectives and design published. 2007, European Ariane 5 rocket approved for JWST launch. 2009, final HST servicing mission, freeing Goddard cleanroom for JWST integration. The early 2010s brought significant challenges and reviews for the JWST project. 2010, CSA redesigns tunable filter imager as NIRICE. 2010, near-infrared detector degradation discovered, requiring replacement. 2010, Independent Comprehensive Review Panel, ICRP, established. 2010, budget assessment indicates need for $8 billion total budget and 2018 launch. 2011, House Appropriations Subcommittee proposes zero budget for JWST. 2011, Congress approves $8.0 billion budget to launch, with cost cap. This period saw the integration of JWST's instruments. 2012, MIRI and NIRICE/FGS arrive at GSFC. 2013, NIR-CAM and NIRSpec arrive at GSFC. 2014, 4 instruments assembled into the ESHIM. 2014 to 2016, 3 cryovac tests conducted on the instrument module. Challenges during this period included a major snowstorm, a lightning strike on the building, and a fire in the clean room. No flight hardware was harmed in these events. The fabrication and assembly of JWST's mirrors was a critical process. 18 primary mirror segments, secondary mirror, tertiary mirror, and fine steering mirror made of beryllium with gold coating. Mirrors polished to meet 25 nanometers root mean squared surface figure requirement at cryogenic temperatures. Individual mirrors completed by early 2012. Assembly of primary mirror segments onto backplane in late 2015 and early 2016. Integration of ESA onto back of primary mirror completed by May 24, 2016. The Optical Telescope Element and Integrated Science Instrument Module, OTIS, underwent extensive testing. May 7, 2017, OTIS flown to NASA's Johnson Space Center. 100-day full-scale cryovac test at Johnson, including during Hurricane Harvey. February 2, 2018, OTIS arrives at Northrop Grumman for integration with spacecraft and sunshield. 2018, loose screws and washers found after sunshield vibration test, causing significant delay. New launch date in 2020 selected as likely. During the 2010s, significant work was done on mission operations. Mission Operations Center set up at Space Telescope Science Institute, STI. Major software development effort for mission operations, science support, and science operations. JWST Science Advisory Committee, JSTAC, chartered to help develop science policies and approaches. JSTAC met for 8 years in parallel to the Science Working Group, SWG. Both advisory committees eventually succeeded by the JWST Users Committee, JSTUC. The final years before launch involved intense preparation and testing, including integration and testing of spacecraft and sunshield, environmental testing of the fully assembled telescope, shipment to French Guiana, and final checks and fueling at the launch site. Despite challenges like the global COVID-19 pandemic, the team persevered to ready JWST for launch. JWST was successfully launched on December 25, 2021, from French Guiana on an Ariane 5 rocket. Key events following launch included separation from the launch vehicle, solar array deployment, course correction burns, sunshield deployment and tensioning, primary mirror segment deployment and alignment, and arrival at L2 orbit on January 24, 2022. The months following launch were dedicated to commissioning the telescope. This involved cooling instruments to operating temperatures, fine alignment of mirror segments, calibration of instruments, capturing and processing first light images, and releasing the first full-color images and spectroscopic data on July 11, 2022. The commissioning phase showed that JWST was performing even better than expected, with improved resolution and sensitivity. JWST's early science observations have already yielded significant results, including detection of galaxies at unprecedented redshifts, detailed spectroscopic analysis of exoplanet atmospheres, high-resolution imaging of star-forming regions and protoplanetary disks, observations of distant supernovae, and studies of galaxy evolution across cosmic time. These early results demonstrate JWST's transformative potential for astronomy. With a potential mission lifetime of up to 20 years, JWST promises to revolutionize our understanding of the universe. Future prospects include continued exploration of the early universe and first galaxies, detailed characterization of exoplanets, studies of star and planet formation processes, investigations of dark matter and dark energy, and synergies with upcoming facilities. JWST's success paves the way for future space observatories, inspiring the next generation of astronomers and engineers.